All right. Well, we can also do a hypothesis test for a population proportion. We had a confidence interval for a population mean and proportion. We've looked at hypothesis testing for a population mean, and now we're going to do a hypothesis test of a population proportion. Okay, so the mechanics of the test are the same. It's just our instead of our test being about a population mean, it's now about a population proportion. So we're talking about the proportion as opposed to the mean. And our test statistic now will just be slightly different, and it'll involve the sample proportion as opposed to the sample mean. Okay. So let's just go through this quick example quickly. So the mayor's office claims that its approval rating is greater than 60%. That will be the proportion of the people that approve of the mayor is greater than 60%. So that is, of course, our alternate hypothesis, that the proportion of support in the population is greater than 0.6. Okay. So to test that, a poll of 300 citizens is taken. Okay. And the proportion of the sample who supported the mayor was 65%. So this is just like with the confidence interval for proportion. P hat was our sample proportion, P was the population proportion, and we use a sample proportion to come up with a range of values for the population proportion. Now we're going to use the sample proportion to test the hypothesis about the population proportion. Okay, so we have a right-tailed test. Okay, our test statistic is computed here. We have the sample proportion minus the null proportion divided by the square root of this quantity, standard deviation of the sample proportions, given under the assumption that the population proportion is P0. Okay, that's going to be a z-test. Okay, so we have a right-tailed z-test, and the test statistic now is just computed using this formula. Right? For us here, the null value for the proportion is going to be 0.6. All right. So a right-tailed z-test. Significance level is 0.1 now. So we haven't seen that before, but we can throw that in now. So that means we have a right-tailed z-test, and our rejection region area now is going to be 0.1. So we're going to reject the null for the most extreme 10% of test statistics now. Okay. So the rejection region is out here. The critical value now, with 0.1 area to the right on standard normal, is 1.28. Okay. Our test statistic computed. Remember, our null value, we're assuming that the population proportion for the test is 0.6, and we're looking to see if our sample proportion of 0.65 is sufficiently greater than 0.6 to land us in the extreme right 10% of all possible outcomes. Okay, our test statistic is 1.77, which indeed lands in the rejection region. Okay, out here. So our test statistic does lie in the rejection region. Therefore, we have statistically significant evidence that the proportion of support for the mayor is in fact greater than 60%. We will reject the null hypothesis. Okay. The p-value will be the probability that the z-value is greater than or equal to 1.77. Probability of getting a result as extreme or more extreme in support of the alternate hypothesis than our observed test result. And that is 0.0384, which again is less than 0.1. So this tells us to reject, and the fact that our test statistic was in the rejection region also tells us to reject the null. Okay, so the mechanics of the test are the same. You still set up your hypotheses. You have a direction of the test. The proportion test draw is going to be z-test. You have your rejection region based on your significance level. critical value, and then the computation of the test statistic is just using a different formula, okay? But everything else is the same, okay? All right, that's a hypothesis test for population proportion. And this, of course, could be two-sided, it could be left-tailed, but at this example, we had a right-tailed test, okay? All right, now let's talk about what can happen when you do one of these tests, okay? So when you do a hypothesis test, you do not know whether or not your null hypothesis is true, right? If you knew if the null hypothesis was true or false, then you wouldn't be doing the test in the first place, right? So you're performing the test under uncertainty, right, about the null hypothesis. Now, but let's suppose that the null hypothesis is in fact true, right? I mean, just because we don't know whether the null hypothesis is true or false, it is either true or false, okay? So if the null hypothesis is true, then one of two things can happen. You could either reject the null, or you could fail to reject the null, okay? If the null is true and you accept it, then you made a correct decision, okay? If the null is true but you rejected it, then that is a mistake, and that type of mistake is called a type 1 error, okay? Now, what about, so the other possibility is if the null hypothesis is in fact false, okay? Now, if you fail to reject the null, even though the null was false, that is also a mistake, and that is called a type 2 error, okay? And if the null hypothesis were false, and you do reject it, then of course you made the correct decision, all right? So if the null hypothesis is true, but you reject it, that is called a type 1 error. If the null hypothesis is not true, it's false, but you accept it, then that of course is also a mistake, and that is a type 2 error. So you just need to get these definitions straight, okay? So let's dig in a little deeper into what this is all about, okay? So let's look at this scenario where the null hypothesis is true, okay? So case 1 is, so this is in the context of a right-tailed test for of a population mean, okay? So mu0 here, true, is saying the null hypothesized value for the population mean is in fact the actual population mean. So the null mean is the actual mean, okay? So here, therefore, would be the distribution of the possible sample means, right? The mean of the sample means is the population mean, which we're assuming is the null value. The standard deviation of the sample means, remember, is sigma divided by root n. So if our significance level is alpha, we will be rejecting for sample means that would land us out in this region, okay? Again, this is not a standardized sample mean distribution. This is just the actual sample means, okay? So null is true. Here is the actual possible distribution for sample means, okay? So I'll ask it this way. If you take a sample and the sample mean lands here, what would the conclusion be? The conclusion would be you would not reject the null, and that would of course be a correct decision, okay? Again, so for this example down here, we're operating under the assumption that the null hypothesis is true, so that the real population mean is the null hypothesized population mean. Okay? So sample landing here would result in a correct decision. But it's certainly possible to get a sample mean that lands out there. Okay? Now the probability of that occurring is, less than alpha. But this would lead to a rejection of the null hypothesis. So even though the null hypothesis is true, we could still reject it, okay? And that would be a mistake, and that is the type 1 error. Now, the probability of a type 1 error would be alpha, and that is the significance level. So what the significance level is all about is it is setting in advance the probability of making the type 1 error, okay? So you set a threshold that you're willing to live with for making a type 1 error, okay? Now, why wouldn't you just make that as low as possible? Well, we'll see in a minute that there's a drawback, a possible drawback there, okay? But generally, generally the significance level is set at 5%. So that's kind of the most common alpha, okay? So here I want to, I'll show you a little bit of a simulation. So we're going to, we have a population which is normal. We have a mean of 50 and a standard deviation of 10 for the population, okay? Now, we're going to take samples from the population, okay, and use the sample to test the hypothesis about the population mean, okay? So our null hypothesis here will be that the population mean is 50, and we're going to have a right tail test alternate hypothesis if the population mean is greater than 50, okay? Our significance level is going to be 0.05, and our sample size will be 30. Okay, so the question here is the null hypothesis true? So is the population mean that we're sampling from 50? And the answer is yes. So we know here, even though it's kind of an artificial scenario, in reality you would never do the test if you knew that the null hypothesis was true or false, right? That would be silly. But here we're kind of, we're being, omniscient, and we're saying we know that the null is true, but we're still going to take a sample and conduct a test, okay? And we're going to conduct 1,000 tests, okay? So what does this say? Okay, so we conducted a test, all right, by taking 1,000 samples, right? And each one of those samples produced a test statistic that either landed in the rejection region or not, okay? So the rejection region here would be, it's a right tail test with a 5% significance. It'd be 1.645 and greater. So what this red is showing here is these are all the samples that produced test statistics that landed in the rejection region, right? However, what percentage of the tests did that happen for? Well, roughly 5%, okay? So we had a null hypothesis that we knew was true, but when we tested based on taking random samples from the population, still almost 5% of them, 5% of those samples led to a rejection of the true null, okay? So by setting the significance level at 0.5, we basically ensured that the probability of rejection, even though the null was true, was at most 5%. Okay, so by setting the significance level, you're putting a cap on the probability of rejecting the null if it in fact is true. Okay, so I hope that makes sense. Okay, so significance level of a test is the probability of committing a type 1 error, right? And you can set that in advance. Okay, now what about the case where the null hypothesis is false? Okay, so here it's a little bit more complicated. So again, we still have a right-tailed z-test. Okay, so what this is, I'm going to make this red. Okay, so remember, we have a null hypothesis. Okay, and the test is based on the assumption that the null hypothesis is true. So we're assuming that the distribution of the test statistics is the red curve. Okay, so our rejection region and our critical value would be right here. Our rejection region is also based on what's called the null distribution. Okay, we think the distribution of sample means is the red curve, and our rejection region is based on the null. Okay, so that's the setup. Okay, because again, we don't know in reality whether the null is true or false, but the test is based on the assumption that the null is true. Okay, so the rejection region is also based on the assumption that the null is true. Okay, now in this case, it turns out that we're going to say it's the case that the null hypothesis is false. And for this example, we'll assume that the null mean is actually less than the actual mean. So mu1 here would be the actual population mean. Mu0 is what we're assuming the population mean is for the test, the null mean. Okay? So what that does is, if the actual population mean is mu1, then the distribution of the sample means in reality is really the blue curve. Okay, this would be for for normal distribution of sample means. Okay, so let's go through a few questions. So my first question would be, you conduct your test, you take a sample, and the sample mean test statistic lands you here. First of all, is that possible? Yes, that definitely is possible. Okay, and what would the decision be if the test statistic, which in this case is just the sample mean, if it landed in the alpha region? Well, that was the rejection region for the test, which was based on the assumption that the null hypothesis was true. In other words, that the distribution of test statistics was the red distribution. So if you got a result that landed in this alpha region, you would reject the null. Okay, and that would actually be, in this case, a correct decision because the null was false. The actual population mean is mu1. So now this would correspond to a correct decision. Okay. Now, what if your test statistic, your sample mean, landed there? Okay. Then what would you do? Well, again, this would lead to the result of not rejecting the null, right? Because remember, the test is based on the red, the test is based on the null, rejection region, acceptance region. So this would be a conclusion of not rejecting the null, even though it is the case here that the null is actually false. So anything landing here in this beta region would be a type 2 error, okay? And the probability of committing a type 2 error is that area, okay? I mean, think about this. Is it possible in this scenario to get a sample mean that lands here? The answer is no, because the null hypothesis is false. So the actual distribution of sample means is the blue curve. So you're going to get sample means in here, okay? So, you know, it's really not realistic to expect to get a result there, okay? So now, you know, theoretically, this really kind of goes on forever, right? It's a normal distribution, so it doesn't really hit the line. But for all practical purposes, you're going to end up with results, you know, between here and there, right? So you can think of this little area here would be your probability of not rejecting the null, even though it is false, okay? And that is a type 2 error, okay? Got it? So beta is a probability of making a type 2 error. And that only is possible, of course, the type 2 error is only possible if the null hypothesis is false, okay? A type 1 error is only possible if the null hypothesis is true, okay? So the scenarios under which a type 1 error and a type 2 error could occur are mutually exclusive. You can only make a type 1 error if the null is true. You can only make a type 2 error if the null is false, okay? Now, here's the other thing is, well, we don't like errors, right? Who likes to make errors? So, you know, let's say we don't like to make we don't want to make a type 1 error. The probability of making a type 1 error is alpha, okay? So why don't we just make alpha as low as we want? Well, the problem is that, you know, we're really blind to whether or not the null is true or false. So if the null is false and we crank down the alpha because we don't like to make type 1 errors, well, what just happened? When we lowered the alpha, we increased the beta. So by lowering the significance level, which is reducing the probability of making a type 1 error, rejecting a true null, you now have increased the probability of making a type 2 error, which is not rejecting a false null. Okay? So these things, these type 1 error probabilities and type 2 error probabilities, there's a tug of war. Okay? So for the same sample size, if you lower one, you're going to increase the other. Okay? So one way to get around that is by saying, okay, well, what are we going to do? We're going to set in advance the significance level, which is the probability of making a type 1 error. Okay. Generally, you know, it's just kind of the convention that type 1 error is seen as worse than a type 2 error, right? You give benefit of the doubt to the null, so you don't want to reject the null if it is in fact true. Okay, false, positive. So you set the alpha, right? And then you can control the beta by adjusting the sample size. Okay, so that's getting a little bit beyond the level of what we have to do in this course, but the way it generally works is the alpha is set first, type 1 error probability, and then the type 2 error probability can be controlled by the adjusting the sample size. Okay, all right. So now what if you got a result for your test in this scenario when the null is false? You get something out here. That also would be a correct decision. Okay, so the area to the right of this critical value here, that is 1 minus beta, and that is called gamma, and gamma would be the probability. So if the blue curve is in fact the distribution of sample means, the probability of correctly rejecting the false null would be the probability of landing in here, and that is called the power. That is gamma. So the probability of correctly rejecting the false null is the power of the test, okay? And that is 1 minus beta, which is the type 2 error probability, okay? So you have alpha, type 1 error probability. You have beta, which is type 2 error probability. You have gamma, which is the power, which is the 1 minus probability of type 2 error, okay? Type 1 error is rejecting a true null. Type 2 error is failing to reject a false null. Power is the probability of correctly rejecting a false null, okay? And if you lower beta, of course, you increase the power, okay? So the pen and the power of the test, so, you know, if you fix alpha, you can control beta and therefore power by adjusting sample size, okay? Now, the power also depends on what the actual difference between the true mean and the null mean are, okay? If the actual mean is farther away from the null mean, then you're going to be more likely to reject the null, right? And so your type 2 error probability is going to go down and your power will go up. If your null hypothesis is very, very close to the actual, right? Then you're going to have a tougher time landing in the rejection region. And so your type 2 error probability is now going to be much greater, okay? And your power, therefore, would be much lower. So the power is a measure of kind of how sensitive your test is to rejecting the null if, in fact, it is false. And that depends on the actual departure of the null from the true value of the mean. And it also depends on the significance level and the sample size. So, okay, but we're not going to deal too much more with that in this class. Okay, what I want you to know is that the significance level is probability of making a type 1 error, and beta is a probability of making a type 2 error, and power is a probability of correctly rejecting a false null. Okay, and that, you know, generally the way it works is type 1 error is given priority. It's set in advance with the significance level, as we've seen, and then the type 2 error can be controlled by adjusting the sample size. Okay? All right. So type 1 and type 2 errors.